bipartite graph. It saturates every vertex of X if and only if this is quite an important matching theorem. I mean, very commonly used in different, this is what is called the theorem on systems of distinct representations, marriage theorem. Assuming, so what is the kind of model that we have in mind? It is a population, heterogeneous population that consists of, so it could be the set X consisting of boys, set Y consisting of girls. Each boy knows or is compatible with a certain subset of girls. You want to, so the bipartite graph can be viewed as a compatibility graph. Is that clear? Every boy knows, not all of them, not all the girls, but certain number of girls. Same thing is assuming that this is a symmetric relationship. Preferably, I mean, I'm taking stand here, preferably you would want to marry off all the boys, which amounts to saying that saturating every vertex of X, okay? To be done in such a way that every boy is able to marry a girl of his choice, okay? So this is a matching, So we want to find a matching, and what this is saying is this is a both necessary and sufficient condition. It need not be necessarily boys and girls. It could even be jobs and the people who give jobs, the firms that can employ these job applicants. So not every job is suitable for every applicant. Every applicant is suitable for a certain number of jobs. Each person should get a job of his choice, and each job preferably should be assigned to one person, etc. So this appears in disguise in many different forms. Hall matching theorem. The necessary part here is easy. It's quite easy to prove the necessity. So let M be a matching. Is it clear that if I have a matching M which saturates every vertex here, it will be a maximum matching, that's clear. You cannot really have a matching better than that, because in bipartite graph, every edge, all the edges are going from X to Y, okay, there are no edges going inside Y. So this is the maximum that you can do. What one is saying is a maximum. Let M be a matching that saturates each vertex. Then, given for every X in X, a unique So, this is as good as saying that one boy should know at least one girl. Is it clear? Otherwise there is no way, if there is a boy who doesn't know any girl at all, there is no way you can have two boys together in the union should know at least two girls. Three boys should know at least three girls, etc. So this is a natural condition. It's a fairly natural condition to ask for. Three boys have to know at least three girls so that I can pair them off. Okay? 10 boys have to know at least 10 girls. So that's exactly what this is saying. So this is a necessity part of it, the easier part of the argument. It is a sufficiency that requires some work. So conversely, let I want to prove that you have a matching that saturates every vertex of X. Let maximum matching. We wish to show that M saturates each every vertex here is on an edge in the matching. So prove by contradiction now. Suppose not. Suppose M unsaturated what we'll prove is that if this happens, then this condition will be violated. This condition will not hold true, and therefore that is a contradiction. That is a contradiction. So there is a vertex here which is unsaturated. What is meant by unsaturated? That means there is no edge of M on U. Is that construct M alternating paths beginning at U. Is it clear? So the very first edge is not in the matching because U is unsaturated. U is unsaturated, we have declared that U is unsaturated. So this you get here. So this is not in M. So the next edge has to be in M. The next edge is not in M, etc., etc. You keep doing that. Let S be the set of all vertices such that X is in X and there exists an M alternating U to X path. Okay, be patient with this proof. This is a difficult part. This is a considerably difficult part. As in all these cases, the necessity part is quite trivial. It's a sufficiency which requires considerable amount of work. Let T be the set of all those Y's u to y path which is M alternating. Then all these paths, they begin with u. They all begin with that vertex u, the unsaturated vertex. In fact, I can tell you how these paths will look like. The first edge not in M, the second edge is in M, third edge is third not in M, fourth in. The way to view this is what is called forward edges. Forward edges not in M, backward edges in M. Forward in, not in M, not in M, not in M, etc. It proceeds that way. Let's make quite a number of claims now. How did a vertex here, look at a vertex here. Can this vertex be, I go over this, not in M, not in M. Suppose this was unsaturated. Just assume that this vertex was unsaturated. Then this not only is an alternating path, but it actually becomes an augmenting path. If this is an augmenting path, then it contradicts the assumption that M is a maximum. Because if you have an augmenting path, then the matching could be made bigger. Then you can get a bigger matching with one extra edge. Therefore, this could not be unsaturated. What does it mean to say that it is not unsaturated? That means there must be backward edge there. And this is true for all these vertices. This is true for all these. If this is in T, look at the definition. If this is in T, then this will be in S. Okay, has to be. For every T, Y cannot for in that case we have an M augmenting path contradicting the maximum, the fact that M is a maximum matching. So for all Y is saturated. What does it mean to say that it is saturated? That means, how did you reach that Y using an edge that is not in M? So you must be going back using an edge which is in M. So where is that X then? Well, that's exactly X must be in S. Okay? And X is not U. That is all. This says that we have an injective correspondence. It's an injective correspondence from T into This on the other hand, look at any vertex here. Look at any vertex here. Suppose that vertex is in S. Why did it come into S at all? Why did you put it in S? Look at the definition of S. Not in M, not in M, in M, etc. Therefore, the very fact that you approached this vertex, which is not equal to U, means you used a backward arc using a vertex which is in T. On the other hand, let x belong to S, x not equal to U, then x is in S implies that there exists an edge where hence we have, so this is not just an injective correspondence, it's a bijective correspondence. Given by clearly, look at any vertex y here. Look at any vertex y here. We already said that it is in the matching. We started moving forward things. Whenever we used forward things, you are going from S to T, T to S, etc. That is exactly what is happening. For all T is contained in N of S, I now want to say that T is equal to N of S. Can it so happen that for some vertex here, what may happen is this vertex here, which is in S, it is adjacent to something. The backward arc is in M, therefore the forward arc is not in M. Then this vertex by definition must have gone into T. Why did I not put into T? That is contradiction. Suppose the fact that x to z but then see, this just means that there is a path that is going up to x. I could have extended it up to z. I could just have extended it all the way to z, and I must include z in that case in T. That is the definition. So, T is equal to N of S. We are done now. We are done because we said that therefore size of t, or rather size of n of s, which is same as size of t, the bijection between t, s minus u and t says that this has the same size as s minus u, whose size is equal to size of s minus 1. Said that this whole thing arose because we said that U is unsaturated. So there is no unsaturated vertex. So if you take a maximum matching, it must saturate everything on this side. And that's exactly the claim. So there is a matching that saturates every vertex. Is that clear? This is an important theorem. This is quite an important theorem. The sufficiency part is a difficult, it's a very tricky argument. So go over it carefully. But has very nice consequences. This has very, very nice consequences. So let's look at some of them. We all know what is a permutation matrix. What is a permutation matrix? Permutation, it's a 0-1 matrix in which on every row there is exactly one entry equal to 1, and on every column also there is exactly one entry equal to 1. Binary matrix. With constant row and column sum. This is standard combinatorics literature. This is called Koenig's lemma. Okay, it's referred to as Koenig's lemma. Proof. What is a binary matrix? 0-1 matrix. So from that 0-1 matrix, I can make a graph. So yeah, a bipartite graph. How do I make a bipartite graph? Construct as follows. Xi yj is an edge then G is a k regular graph because the row sum is k, column sum is k. So every vertex, yes, what happened? Is that clear? So We want to show that G has a matching which saturates every vertex of X. If G has a matching which saturates every vertex of X, the same matching will also saturate every vertex of Y, because X and Y in this case have the same size. This is a symmetric situation. This is as good as saying you have the same number of boys and same number of girls. Okay? Okay. Nice situation. So perfect pairing is possible in that case. A perfect matching. Which is same thing as, that is a matching which saturates each vertex what that Hall matching theorem is saying is, sufficient condition for this to happen is take some set of vertices here, in their neighborhood you should have at least so many vertices. So let how many vertices do I have here in X? R vertices. Each one of these is adjacent to how many vertices in Y? K. So make a two-way counting. Make a two-way counting. That will give me the total number of edges coming out of these will be K for this, R multiplied by K. RK edges will be coming out exactly. On that side, who is receiving these edges? That is what we call N of S. That's exactly the neighborhood of S. Y is adjacent to at most is that clear? You see, if I have a Y here, it doesn't have to be adjacent to, it is totally adjacent to K vertices, but they don't have to be here, all of them. It may be adjacent to some vertices outside S. Okay? So it's no more than K. Using a two-way counting, size of N of S multiplied by K. Therefore, the condition there, the Hall condition is satisfied. That condition is satisfied. Therefore, there is a perfect. Therefore, there is a matching that saturates every vertex here. Such a matching is a perfect matching. It saturates every vertex. Hence, we have a required matching. What does a perfect matching in case of bipartite graph do? It pairs vertices up. See, this is the whole idea. So x1, x2, x3, xn, these will be, x1 will be paired to some unique fellow here, x2 paired to something here, by definition of perfect matching. So that perfect matching actually corresponds to a permutation. We have seen this earlier. So it corresponds to a permutation. Removing this perfect matching from that graph, the graph consists of edges. Every vertex, the degree is k. If you remove that perfect matching from this graph, what I will get is a graph in which each vertex has degree k minus 1. Therefore, I can just proceed by induction. Let M be a perfect matching is k minus 1 regular so inductively okay. I will leave this to you. Complete the translation from graph to matrix. Okay. That is all that is required. Yeah. So what is the, if I have a set of n boys and n girls in which every boy knows k girls and every girl knows exactly k boys, where k is a positive number, then it is possible to pair them off in such a way that each boy can marry a girl of his choice and each girl also marries a boy of her choice. Okay? That is what this theorem is saying. So this is a very nice thing to, this is a really nice thing to have, a pleasant consequence, expected line. A slightly more involved thing here is, let me touch on that also. So, because this is required in other areas of mathematics. Definition. Real matrix. Non-negative entries, then A is called a doubly stochastic matrix. If so all the row sums are equal to 1 and all the column sums are also equal to 1. Yeah, what would be example of a doubly stochastic matrix? Okay, that's a doubly stochastic matrix. Is it clear? I have deliberately written irrational numbers just to make a point. Is it clear? That's a doubly stochastic matrix. These matrices occur naturally in the setup of where they are quite important. People who work in probabilities, these matrices are payoff matrices. If there is gambling happening between n people, these are sort of probabilities associated with this. That's exactly why we need this condition. So this is a natural object. Doubly stochastic matrices occur naturally in the various other branches of mathematics, namely probability, statistics, Markov chains, such kinds of things. These matrices occur very naturally. A good example of a doubly stochastic matrix is a permutation matrix itself. Every permutation matrix is a doubly stochastic matrix. So there are plenty of doubly stochastic matrices. In a vector space, what is the standard thing? What does one call a convex combination? What is a convex combination? If I have a set of m vectors, let's say, a convex combination, if I have convex hull, that's correct, that's exactly what I'm. Non-negative, is that clear? This geometry here. What kind of geometry do you have? You have one vector here and other vector here. The line joining them, you're looking at all the vectors. This is what many times is also expressed by saying lambda v plus 1 minus lambda w, okay, where lambda takes values between 0 and 1. So this is the line segment that joins, it's a line segment, so it has a finite length. It has a finite length, in fact. Yeah, in fact it's homeomorphic to a closed interval on the real line. When you take convex hull of 3 points, it is a triangle. It is actually a closed triangle like this, unless of course V3 also happens to be on the line V1, V2. If V3 happens to be on the line V1, V2, then you'll just get line segment, but this is sort of a general picture. In general, if I have n points in general position in plane or in space, I need to take a convex hull of these. Is that clear? So the geometry is something that you have to imagine. A convex hull of finite set of n points will have these points at the corners of a convex object, convex polytope, in which these things will be corners. So the theorem that we are looking for is look at the set of doubly stochastic matrices. The theorem says that I can write every doubly stochastic matrix as a convex combination of permutation matrices. This is quite an achievement in the sense that if you look at the definition of doubly stochastic matrices, this is too general. Even 2 by 2 doubly stochastic matrices will be uncountably many. Is that clear? Far too many doubly stochastic matrices. Whereas even n by n permutation matrices are only n factorial number. Those are finite. Number of permutation matrices is finite. For every n, number of permutation matrices is a finite number. It's large but still finite. Okay? So what we are saying is the set of all doubly stochastic matrices is convex hull of permutation matrices. Okay? Take 2 permutation matrices. So one by one, if P is a permutation matrix, Q is a permutation matrix, convex combination is doubly stochastic. This is quite easy to see. Because what is it that I will be doing? Lambda times p plus 1 minus lambda times q. The row sum here is equal to 1. Therefore, row sum combination of permutation matrices, it's a doubly stochastic matrix. What is not obvious is the converse. I give you a doubly stochastic matrix. How do I know that it is a convex combination of permutation matrices? So that is exactly what the theorem is saying. So let's write this out. This is called the Barkov-von Neumann. Then A is a convex combination The proof is similar to this but lot more elaborate, because now we are dealing not with 0-1 matrices but with matrices that have non-negative real numbers. So we have to be careful with this. Sorry? Huh? Yes, that's exactly what we'll do. No, in fact, whenever there is a positive entry, we'll join. Is that clear? That's exactly what I'll be doing. Okay. Now, all right, it's started thinking about it. How many positive entries must be there in each row of A? At least one. Is that clear? Is that clear? At least one. This is true for every row. For every row, you must have at least one positive entry. So at least one cell, because that is the condition given, the total is equal to 1. How can everything be equal to 0? That just so in every row, there is at least one cell where the number is positive. Therefore, the total number of positive entries in that doubly stochastic matrix is at least equal to n, counting over all the rows. In each row there is one positive entry. When will it be equal to n exactly? When it is permutation matrix. Because it will be equal to n, I can go back, I look at the argument again. That means in every row there is only one entry which is positive. Now if that one entry is going to be positive, it has to be equal to 1. There is no question, it must be equal to 1. Okay? That means you are in a very peculiar situation that only n entries are positive, they are all equal to 1, and in every row there is exactly one of that kind. That's exactly what we call permutation matrix. Therefore, the least number of positive entries in any doubly stochastic matrix is n with equality if and only if it is a permutation matrix. This theorem of course is true in case A itself happens to be a permutation matrix. That there is nothing to prove in case A is a permutation matrix. Is that clear? I mean, it is like saying A is equal to A. Yeah. Because because this itself is a permutation matrix. There is nothing to prove in that case. So proof. Okay, here by non-negative matrix I mean matrix in which every entry is non-negative. Okay, it's used very commonly by matrix theorists. Let C of A, content of A, cardinality of the set Ij such that Aij if A is doubly stochastic, then content of A with equality if and only if a permutation matrix. Therefore, this proof will proceed by making induction on content of A. Thus, least content is equal to n. The largest content could be n square. There are as many as n square cells there. All of them could be positive. Okay. We now make induction where the assertion holds so let content of A is strictly larger than n. As somebody suggested, the proof exactly is based on drawing a graph. You have to draw a graph. Draw a graph, a bipartite graph. Xi Aij is positive. If I can show that this graph has a perfect matching, suppose I succeed in showing that this graph does have perfect matching, let's see what that amounts to saying. I mean, suppose this graph has a perfect matching. Suppose it is a 4 by 4 situation. What that means is, it's as good as saying that I can find 4 entries on that matrix such that this is positive, this is positive, this is positive. Is that clear? That's what it amounts to saying. Four cells with the property that these 4 cells, no 2 are in the same row and no 2 are in the same column. Such a thing is called a transversal. This is exactly what is called. So this corresponds to actually a permutation. It actually corresponds to a permutation. I would like to leave this to you to show that this graph has a perfect matching. Show that this graph, based on the properties of doubly stochastic, we have to use the properties of doubly stochastic matrices, okay, and Hall matching theorem. A1 sigma 1, A2 sigma 2, that's exactly what I'm saying. They are all positive. So this is a positive number, this is a positive number, this is a positive. They are all positive numbers. No. There could be several other positive entries. That's correct. That's exactly what I would do. These are all positive numbers, so there will be smallest among them, the minimum among them. If you have a finite number of positive numbers, the smallest is a positive number. Something that doesn't hold for infinitely many. We know that. Infinitely many positive numbers, the smallest may not really be, that's not true. Mathematics students should know this. That's not the correct statement to make. But when I have a finite number of things, there is no problem. Let T is positive. I construct a permutation matrix now. Pi sigma I is equal to 1. If j is not equal to sigma I. Yeah, I mean, you just take those entries. What is it that I would do now? I would subtract the suitable multiple of P from A. Let what are the row sums and column sums in A? They are all equal to 1. What are the row sums and column sums in P? They are all equal to 1. Therefore, what are the row and column sums here? They are all equal to T. Therefore, what will be the row and column sums in B? They will be equal to 1 minus T. Can T be equal to 1 really? Let's see that. T is equal to 1, then it's a permutation matrix. So we can even say that T is strictly less than 1. Then B has row and column sums equal to 1 minus T, where 0 is less than 1 minus T and 1 minus T is less than 1. T is not equal to 1, T is also not equal to 0, T is a positive number. Main thing here is B is not doubly stochastic, B is of course not doubly stochastic, the row column sums are equal to 1 minus T. Whereas in order to apply induction, we want to use induction. B should look like a doubly stochastic matrix, which it is not. B is not a doubly stochastic. What can one say about the content of B? Content of B is at least one cell, the entry is killed. It gets killed because this minimum would occur somewhere. It would occur somewhere. So the content of B is strictly less than content of A. Let C be the matrix which is obtained by multiplying 1 B by 1 reciprocal of 1 minus T. then C is doubly stochastic, no problems. So I can write C as a convex by induction. Permutation matrices. This is convex combination. Now we just need to go back. From C I get B. So how does B look like? B is equal to 1 minus T into C, which is equal to 1 minus T into A1 P1 plus A2 P2 plus AR PR. And finally, how is A obtained from B? So here now A itself is equal to T into P plus B. Where check that this is actually a convex combination. It is T plus 1 minus T into A1 plus 1 minus T into A2 plus 1 minus T into, because A1 plus A2 plus is equal to 1. So this, the coefficients add to 1 minus T plus T, that is equal to 1. So this is a convex combination. This is a convex combination with R permutation matrices. So this is a convex combination with R plus 1 permutation matrices, and therefore we are through. That's a very powerful theorem. If you look at the set of all doubly stochastic matrices, n by n doubly stochastic matrices, they, where do they sit? They sit in a space with dimension n square. They sit, n by n matrices are part of and what it is saying is this is a convex object whose corners, so it's like a convex polytope in Rn square, the corners of this convex polytope are permutation matrices. So this has finite number of corners. Is it clear? I mean, convex objects don't have to look like a cube. Okay, is that clear? Cube is convex, but so is a sphere. Okay, so sphere doesn't have a finite number of corners the way cube has. These are very different convex objects. So what this is saying is the set of all doubly stochastic matrices is sort of like a cube. It is like a cube in n square dimensional space. It's not quite like an ellipsoid or that kind of object. So that's what the Markov von Neumann theorem is saying. So we'll stop.